In this section, we return to the question of indeterminism, but now we ask specifically whether brain function is in any sense indeterministic. Even if the universe is indeterministic at the level of the quantum domain, it might make no difference at all to brain function, since, according to modern physics, the only domain that is inherently indeterministic is the quantum domain. The only way that the macroscopic domain of neurons can be made indeterministic is if there is amplification of indeterminism from the quantum domain to the macroscopic domain of neurons. Here, we'll examine evidence for the amplification of microscopic indeterminism to the macroscopic domain of cell activity. I'll give numerous examples of such amplification, but even if there were only one such mechanism of amplification, it would suffice to make the behavior of the brain indeterministic. And if even one tiny corner of the universe, such as our brains, is made indeterministic by such amplification, then the entire macroscopic universe is made indeterministic because we are agents acting in that universe at the macroscopic level, changing things in light of our creative thoughts, whether building airplanes or even just choosing to make this for dinner versus that. In a previous section, we considered the Brownian motion or random walk of neurotransmitters as they diffuse across the 20 to 40 nanometers of the synaptic cleft. This is one way that randomness from the microscopic domain is amplified to the macroscopic domain of spike timing. Let's look at Brownian motion a little more closely. Here's a movie of a particle of dye in water. The yellow trail indicates the random walk of the particle, and the box is meant to help you disambiguate where it is in 3D space. A bigger molecule might move around like this, and 5 particles might move around with blue trajectories like these. The red arrow here indicates the moment-by-moment velocity of one of those particles. Brownian motion was noticed by a botanist named Robert Brown. In 1827, he noticed that particles of pollen floating in water seemed to jump around. Because the water itself had no net direction of flow, since it was in a jar, this was thought to be very strange. At first, he thought it might have something to do with the particles of pollen being alive, like little Mexican jumping beans. But when he put tiny inert particles into water, he saw the same motion, ruling out the hypothesis that being alive had something to do with it. It was Albert Einstein who finally gave a formal explanation in one of his 1905 papers. Basically, particles bump into the other particles in which they are suspended, which then move the particle around. Einstein was able to infer the size and number of atoms in a medium by looking at the magnitude and frequency of jumps of a particle. Now, you might think that only a genius like Einstein would be able to explain something as seemingly mysterious as Brownian motion. But no, it was figured out long, long ago. In a remarkable passage from 60 BC, the Roman thinker Lucretius gave the correct explanation of Brownian motion. Here's a passage from verses 113 through 140 of his book On the Nature of Things. Observe what happens when sunbeams are admitted into a building and shed light on its shadowy places. You'll see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of underlying movements of matter that are hidden from our sight. It originates with the atoms which move of themselves. Then those small compound bodies that are least removed from the impetus of the atoms are set in motion by the impact of their invisible blows, and in turn cannon against slightly larger bodies. So the movement mounts up from the atoms and gradually emerges to the level of our senses, so that those bodies are in motion that we see in sunbeams, moved by blows that remain invisible. Wow. Lucretius is saying here that there is amplification from an invisible domain of colliding atoms up to a level of macroscopic particle movements that we can see with our naked eye. and so it is in the synapse as well. Brownian motion affects the arrival time of neurotransmitter on receptors such as AMPA and NMDA receptors, which in turn affects the timing of the opening of these ionotropic pores, which in turn affects the timing of an excitatory postsynaptic potential, which in turn affects the timing of an action potential, which in turn affects the timing of coincidences of action potentials reaching a postsynaptic neuron, which in turn affects whether the postsynaptic neuron will fire. You have all heard that a butterfly's wings flapping can in principle influence the formation of a storm if amplified in just the right way. Here, the butterfly's wings flapping might be as subtle as the random motions of a molecule of glutamate in the synaptic cleft. Brownian motion in the synaptic cleft alone is a sufficient mechanism for amplifying randomness from the atomic domain up to the domain of neural spike timing. With this mechanism alone, the entire macroscopic universe might be made indeterministic because our activities in the macroscopic universe are influenced by the amplification of random movements in the nanometer regime of the space between our neurons. But there are other mechanisms where the activity of a single atomic particle is amplified up to a level of spike timing randomness. Another example can be found in the NMDA receptors that we have been discussing. Remarkably, they are blocked by a single atom of magnesium, a bit like a stopper might block water from flowing down the drain. In the background here is an animation showing how ions flow into AMPA and NMDA receptors. When glutamate binds to an AMPA receptor, sodium ions can flow into the cell, depolarizing it. We've learned that 3 facts have to be true for the NMDA receptor to open in turn. Glutamate has to bind to it. D-serine or glycine has to bind to it as well, and in addition, the postsynaptic neuron has to already be depolarized because AMPA receptors recently opened. If all of these facts are true, the magnesium ion, shown in this animation as a brown stopper, will drift out of the pore, freeing calcium ions and other ions to enter a dendritic spine, depolarizing it much more massively than is possible with AMPA receptors alone. But the departure of the single magnesium ion from the pore is a quantum domain effect whose timing is indeterministic. It can only be modeled as a random process. So, in addition to Brownian motion of neurotransmitter molecules, such as glutamate across the synapse, we now have a second way of amplifying quantum domain indeterminism up to a level of spike timing indeterminism. But NMDA receptors may amplify quantum domain indeterminism to a level of indeterminism in neuronal spike timing in an even more interesting way than the timing of the release of the magnesium ion from its NMDA receptor pore. NMDA receptors may play a role in placing the operation of the brain in the domain of criticality, the sweet spot that balances dynamic excitation with inhibition occurs in a narrow range of moderate excitability. Theoretical work suggests that dynamic systems are maximally perturbable even for small inputs when the system operates in the narrow zone of criticality, which, theorists have shown, in turn requires a baseline spontaneous firing rate. The criticality domain expresses a moderate mean level of synchrony with maximal variability of synchrony. This domain lies at the boundary between excessively low synchrony and excessively high neuronal synchrony in the population of neurons. The healthy brain, therefore, appears to operate where unpredictability of network response to a given input is maximal. This high variability, borderline chaotic behavior of healthy neural networks may account for empirical evidence showing variability in neuronal responses to identical external inputs. Some theorists have argued that the brain's operation in the domain of criticality may arise in part because of the nonlinear and burst-triggering responses of NMDA receptors. If information is carried in perturbations of firing rate away from the baseline firing rate, this domain is maximally sensitive to perturbations and thus is maximally capable of carrying information. In a sense, the system is set up so that the fluttering of a butterfly's wings, which is a metaphor for local fluctuations or variability in spike timing, can be amplified up to a level where it makes a difference to information processing in the brain. In this section, we have considered 3 ways that microscopic indeterminism can be amplified up to a level of spike timing indeterminism, namely Brownian motion in the synapse, magnesium ion behavior in NMDA receptors, and then the introduction of criticality or near chaos in neural spike timing, again, probably by virtue of NMDA receptor behavior. I think that is enough to make not only our brains, but even the whole macroscopic universe indeterministic. But some people have argued that there are even stranger ways that quantum domain indeterminism might play a role in brain function. I have to say I'm skeptical of this, but we will cover these possibilities in the next section.